determine the domain of each function. So I want you to give me the domain of each of these functions. This is a radical graph. So remember radicals, we know what can't be under a square root. Starts with an N. Yeah, I thought I was going to have to say rhymes with negatives, but you got there. Negatives. Negatives can't be under a square root. And then this is a rational. What's our problem with rationals? The bottom can't be equal to 0. So your denominator has restrictions, right? So you could have asymptotes, you could have points of discontinuity, if things cancel off, stuff like that. So that's what we're going to look for. So remember, the domain is restricted in places. So we're going to try and come up with the domain of this one and the domain of this one. See if you can do it out using your calculator. So we know under a radical, we cannot have a negative number. That is a statement that is true. So we know that what is underneath our radical has to be at least greater than. People don't know if it's greater than or equal to. Remember, if you're memorizing something instead of understanding it, there's a chance you're going to oopsie. So let's see why we do what we do. So if we just say use x plus 2, I need a marker. So we have x plus 2, what's underneath that radical, and we said it has to be positive, correct? It can't be a negative number. So we put greater than 0. Some people are like, I don't know if it can be equal to or not. Well, let's think about it. If I take that value and I say, okay, greater than 0, I put a positive number in here, square root of a positive number is fine, correct? What about square root of 0? Is that okay? Yes. If you don't know, you could still solve it out. You subtract your 2 over and you get x is greater than negative 2. So if I put in anything greater than negative 2, I plug in a negative 1. I get negative 1 plus 2, I get 1. Square root of 1 is 1. That's good. If I don't know if it's equal to, I just plug in what it's equal to and see if that works too. So I plug in negative 2. Negative 2 plus 2 is 0. Can I take the square root of 0? Yes. So it can also be equal to negative 2, correct? It also is greater than or equal to 0. Anything underneath a radical sign can be positive and it can be 0 because you can take the square root of 0. Okay? The other way we could have looked at this is a basic radical function. Your parent function starts at 0, 0, and it goes up and to the right. So the parent function is normally x is greater than or equal to 0. A parent function meaning y equals root x, no transformations, right? And we're moving this one 2 to the what? Left. So now what is it? X is greater than or equal to negative 2, right? So you could use transformations as well. I keep bringing transformations up because I don't want it to fall out of your head. Because if you go to university, I want you to be over-prepared, not under-prepared. So if you walk in and they take a calculator away from you, you can still do the stuff. Okay? So these are two ways we could look at this. So in set notation, I still am going to write set notation because, yes, the textbook uses it, and yes, most profs use interval notation. But I'm going to keep set in there just in case prof throws you set notation. We don't want that to go away as well. But I'll accept interval. So set notation would be x such that x has to be greater than or equal to negative 2. And then all those x values are elements of reals. So that means I can have decimals. That's why we follow behind with the real numbers. Okay? In interval notation, it would be greater than or equal to negative 2. So I'm equal to negative 2, round bracket, and then to infinity, or square bracket, sorry, and then a round bracket because you can't equal infinities. The next one is much more complicated in writing it actually in interval notation. Set notation is where people would actually want to pick for this one most of the time. So I can factor that denominator, and I get 1 over, I take a GCF out, and I get x minus 1. So I know x can't equal 0 because of this one, and I know x minus 1 can't equal 0, add that over, and x can't equal 1. Are these asymptotes or points of discontinuity? Asymptotes, did they cancel off? Did the numerator and denominator factor cancel? No, so they're not points of discontinuity, so they're vertical asymptotes. Okay? So, set notation is easier. I do x such that it just can't be those. So I say x can't equal 0 and 1. So in set notation, we always start off with our restriction. It can't be this, and then everything else can be. So that's why we have to follow behind us. We say x can't be 0 and 1. If I stopped here, are the rest of the numbers integers? Are the rest of the numbers real numbers? Are the rest of the numbers natural numbers, whole numbers? What are they? So that's why you have to continue on with that x is an element of the reals, not just because your teacher makes you write it every single time. It's because x can't be 0 or 1, but x is an element of the reals. So what does that mean? It means every single decimal exists in this world, and 0 and 1 are out. That's it. Okay? Now, in interval notation is literally just a way of representing a number line. That's all it is. So if I did this in a number line, my number line would look like this. Negative infinity would be here, 0 would be here, 1 would be here, positive infinity would be here. I don't have to write positive, but I'm doing it to prove a point. What doesn't exist is 0 and 1, correct? So I have open dots there. This exists because this element is real, so everywhere else exists. That's why I have this part, right? And then you just do interval notation represents a number line. Every single one of those intervals, it gets you a new interval. So I'm going to do round bracket, negative infinity, comma hits in the middle, 0, open dot, so I get a round bracket. See that? Then I have a space. Okay, I'm going to put something in that space. Then I have 0 to 1, both round, and in the order of the number line, because they're round because they're not equal to, and then another space, 1 to infinity. Interval notation just represents a number line. That's all it is. If you took that x-axis and you took your domain on your x-axis of a graph, that would be interval notation. Now you have to remember to put unions in between, which are little u's. Because union means or. So I could be here, or I could be here with the graph, or I could be here. So you put little unions in between now. Okay? So basically, interval notation represents your domain on the number line. That's all it is. Okay. Everyone have that? Next page. Piecewise functions. So I'm hitting up all of the previous material that you've learned in other classes that you're going to need for calculus. Okay? Piecewise functions you actually learned when you did absolute values in 20-1. Okay? You would take a graph of a quadratic, and then you take the absolute value of that graph, and it would make whatever was negative y values, positive y values, and then you'd have to give piecewise functions. This and this made this piece and this piece. There was no function that represented the whole function, other than that absolute value sign, but you could write it as pieces of functions. Okay? So here we have a piecewise functions are defined by different formulas in different parts of their domain. So for example, there's not one equation that is going to represent this graph. This graph is f of x. So f of x when 1 minus x, I'm going to draw the graph 1 minus x for all x values less than or equal to -1. So I could technically draw the line 1 minus x. I could draw that whole line, but I would erase everything that's greater than -1, right? Because it doesn't exist. It stops it. That's what it says. So from negative infinity to -1, I draw the line 1 minus x. Then I can draw the whole parabola, x squared, parent function, 0, 0, 1, 1, 2, 2, 2, 4, 3, 9, etc., blah, blah, blah. But I have to actually erase all the graph that is less than -1, correct? And at -1, I would actually have an open dot because it's not equal to. So you could technically draw the entire graph, but you'd have to erase the part of the domain that doesn't exist because they were giving you restricted domains on pieces of the graph. Okay? So we're going to go through and we're going to sketch this one first. So I'm going to go x and 1 minus x here, because that's just my y. My y is represented by 1 minus x. And the domain restriction for this one is x is less than or equal to -1. So I always start at the most restricted piece and then work my way whichever way I have to go. So I'm going to start at -1, because that's where the domain is restricted at. And then I'm going to pick values less than it, because that's what it says I have to do. Okay? So I pick -1, and I plug that in. I get 1 minus -1, and that actually equals 2. And then for my own little welfare, I'm going to say closed dot. Why am I going to say closed dot? Help myself out. What's my domain? Equal to -1, right? So I'm going to have a closed dot at that coordinate. Now I need to pick domains that are less than or equal to -1. So I start at -1. Where should I go to next? X equals what? Starting at -1, I need to go less. You do -2. Then I go 1 minus -2, and so it gets me 3. So I can plot these, correct, down here? So I can go -1 and 2. First, sorry, you should do this. X scale 1 So that the person marking it knows that you actually made those all be 1s. You're not going 1, 2, 3 like we used to do when we were in elementary. And then y scale of 1. Or it could be 2s, or it could be 4s, it could be whatever, but you have to let them know. If not, you have to put little numbers, which that is not the best thing to do. Okay? So we have -1 and 2, close dot. Then we have -2 and 3. Then we have -3, 1 minus -3 equals 4. And it's a line, right? It has a slope of -1 over 1. So you could go down 1, right 1, or you could go up 1, left 1. So you're going to end up getting this. Could I have sketched the entire graph? Could I have went, don't do this, but could I have went y-intercept of 1, down 1, left 1, down 1, left 1, sketch the whole graph? Could I have sketched the whole graph? Yes, but I would have to have erased the blue, correct? Because this graph only exists where x is less than or equal to -1. So you could have drawn the whole thing, but then you would have to go back and say, this doesn't actually exist. Right? Okay, our next one is the graph of y equals x squared. So our y is x squared, and our domain is x is greater than -1. So I'm still going to start at -1. However, it's going to be a what? An open dot, because it's not equal to it, correct? I still have to get that -1, because that's where the graph butts up to. So I do -1, and then I do -1 squared, which is 1, and I go there and I plot -1 and 1, but I have an open dot. And I have to go to the right of it, correct? Because it says x is greater than -1, so what value would I pick next? 0. 0 squared, 0. Makes sense, because this is the graph of y equals x squared. Yes? You know what that graph looks like. You inspected it miserably in grade 11 a lot. It was like a lot of quadratics. Okay. And then 1 squared is 1. And then 2 squared is 4. And then 3 squared is 9. And so I get a graph that looks like this. Do you see how many plotted points I put? You need to do that. You can't just do like 2 and then willy-nilly draw. If your graph looks like you were on a bus and the bus was going over a speed bump, and then you were drawing the graph at that very moment, that is not a good graph. Okay? Your graph needs to be accurate. If anyone's in my class, you've heard that bajillions of times. I have knocked down your graphs relentlessly. Okay? Dots connect well. Okay? If I kept going on this green, it would be, don't do this, it would go like that, right? But that doesn't exist on this graph. Go away. Go away. There we go. So that is actually the representation of f of x equals 1 minus x. This is that. That is the equation to that graph. See what I mean? It gave us 2 equations that gave us 2 pieces that drew a graph. Now, sometimes you get 3 equations. Well, that would be still a piecewise graph. I would just have 3 different graphs in a restricted domain in different restricted domains. That would sketch me 1 graph. So some people say, well, this is 2 graphs. No, it's not. This is the graph of that function. You see how it has one f of x here? That is the f of x function, and it's represented by those equations. So some people say that's two graphs. It's not. It's one. That's the graph that makes up this f of x. Okay? It just has pieces that form that one graph. All right. So we have to answer these questions here. So it says evaluate f of negative 2. So if I were to go onto my graph and find f of negative 2, now that I have it drawn, I would go, okay, negative 2 matches with, didn't need to draw a line. Negative 2 matches with what y? 3. So my answer would be 3. That's if I have a graph sketch. If they just ask me f of negative 2, I don't have to sketch the graph. I can use the equation. You just have to figure out which equation contains negative 2. So if I look at these two equations, which of these equations has in its domain negative 2? 1 minus x or x squared? 1 minus x, because it has x is less than or equal to negative 1. So negative 2 would fall in this domain here. So I would use that equation, correct? So I don't need a graph. I could just go to that equation. And so if they wanted me to actually solve it algebraically, I would go, okay, f of negative 2 equals, I'm going to plug it into here, 1 minus negative 2. So it equals 3. So this would be algebraically how I would have to show it. Okay? And I wouldn't have to sketch the whole graph. So really you only have to sketch piecewise function if it says sketch piecewise function. So if I go to negative 1 closed dot would be 2. Do you see that? Negative 1 is 2. Which equation, which of those domains includes negative 1? The first equation, the top equation, or the bottom equation? The top, because it has a equal. Yeah, that equal to sign, right? So it includes the negative 1. So I would plug it into that equation. So I go f of negative 1 equals 1 minus negative 1, which is 2. F of 0. F of 0 is 0. Which equation's domain represents the 0? The top or the bottom? Which one of these contains 0? X is less than or equal to negative 1, or x is greater than negative 1? The bottom one, x is greater than negative 1. This one includes 0. And by the graph, you can see it includes 0, because the green graph is the second one, right? So I'd plug it into the second one. So I'd say f of 0 equals 0 squared, which is 0. Same answer. Okay? So those are piecewise functions. We talk about them very generically in 11, just kind of with absolute values, and most often than not, people just memorize what they have to put and then switch values, and they don't actually know what they're doing. But they just put a negative sign in it, because they don't understand reflections. Okay, so here, I'm now giving you a graph, and asking you to determine the piecewise function. How many pieces make up this graph? How many different graphs make up this graph? Yeah. Could be 2. If you use an absolute value, or it could be 3 if you use lines. Neither is better than the other. If you use lines, this would be part 1. This would be part 2. This would be part 3. If you do absolute values, you need to realize that there's a reflection in it, and then it's transformed over, which most people won't get. And moved up. So it would be absolute value, negative absolute value of x minus 1, absolute value plus 1, which most people won't get that equation. So it is lines. So I'm going to do it as lines. So how do we break this up? F of x equals squiggly bracket. If you do this, no one's judging you. Just don't do this and don't do this, because those are totally different things. Okay? You're not being judged on your bracket. You will be judged on your equations. So let's talk about the restricted domains first. If I do part 1, part 2, part 3. Okay? Part 1, what domain is it restricted between? 0 and 1. And it actually is inclusive here. Okay? So this is when you're getting to make the equations, you get to make the choice. Are you going to make 1 be inclusive with this one, or 1 be inclusive with this one, or you could make it be inclusive of both, right? You could put the equal sign on both of those domains if you really want to. Either way, I'm going to make the first domain be between 0 and 1. So I'm going to say I have to write myself some equation here. You're not going to actually really have to write a line. I'm putting a line as a placeholder. If 0 is less than or equal to x is less than or equal to 1. And I should figure out what that equation is, okay, which we'll do after. We're just going to restrict the domains first. Part 2, second equation. Looks like a D, but it's a P. Part 2. So I'm going to get an equation of some sort if, now what's my domain restricted between? 1 and 2. 1 is less than, x is less than 2. I'm going to not put equal to signs on it. You could. I'm not even putting equal to signs because I'm going to make the equal to be on this equation and the equal to be on that equation. They don't often put them on all equations, so pick something to put on. So I can either put the equal to here, or the equal to here on the 2, or I can put the equal to here and not put it here, put the equal to there and not put it there. They don't put it on all of them. And then our third equation is if, what's this one? This is 2, and then it goes on, and then there's an arrow. So what do we say? If x is greater than or equal to 2. Now, how do we come up with the equation of the lines? Well, I just draw the line longer and then find that. So if I extended this green one to be this line, this would be the line it would represent, but I'm just only keeping between 0 and 1. Do you see that? I'm actually drawing this whole line here. What would the equation of a line be? Well, I do y equals mx plus b, correct? B is the y-intercept. What's my y-intercept of this line? 0. So I would go plus 0 at the back of the equation. Do I actually have to put plus 0? No, I'm doing that to prove a point. And then I need my slope, correct? What's my slope of this line? Well, if I start at the y-intercept, I have to do what? Up 1 over 1, which is 1 over 1, which is 1. That's the weirdest way to write that equation. How could I just write the equation? X. So this is not wrong, but they will write it as just x. Right? Because it's just the line, just the identity line. 0, 0, 1, 1, 2, 2, 3, 3, negative 1, negative 1. Right? It's just that line. Okay, so I'm going to erase that because I extended that one. So we're done part 1. Now part 2, I'm going to extend purple. So that would be the line for part 2, correct? So what's its y-intercept at? 2. So I'm going to go plus 2 at the back. And then what's my slope? Down 1? Right 1. So what does that result in? Just negative 1, correct? So I'm going to get negative 1x. Or I could have just wrote negative x, because that's the same thing. Right? Your last equation is the easiest. Most often done wrong, but the easiest. It's a horizontal line. Horizontal lines are just y equals 7, y equals 5, y equals 2, y equals 3, y equals, because y equals 7, I go to 7, I draw a horizontal line. Y equals negative 1, I go to negative 1, I draw a horizontal line. Y equals 3, I go to 3, and I draw a horizontal line. Correct? So for part 3, we're drawing this. That is actually the x-axis, isn't it? What's the equation of the x-axis? What is 0? Nope. Y equals 0 is the equation of that x-axis, right? So I'm literally going to go f of x equals 0. And that will get all my pieces, right? I don't often ask a question where you have to make the equation from a graph. But I want you to be prepared that if a prof makes you do that in university, you can do it because you've seen it. I want to over prepare, not under prepare. Okay? More often than not, mine will be, I give you the equations, you have to pick me out a graph. Okay? All right. Symmetry. This comes up in calculus all the time. It doesn't come up in previous information. Like you guys talk about symmetry. You talk about like a quadratic is symmetrical about the y-axis. So if you have the x squared graph, it's symmetrical about the y-axis because it's the same on the right as it is on the left. If I folded it in half, I would get the same graph. It's just like when you did hearts in kindergarten and you folded your paper in half and then you cut out half a heart. It was symmetrical about the y-axis being if you drew it on a Cartesian plane. You just didn't know that because you were little and you were just making hearts that were symmetrical. Okay? So, if a function f satisfies f of negative x equals f of x for every number x in its domain, then f is called an even function. In university mathematics courses, you will be given theorems like that all the time, and you will sit and go, I have no idea what you just said. Okay? So instead of getting overwhelmed, you have to stop yourself and try and decipher what the heck you just read, because they will give you theorems, proofs, corollaries, and you have to be able to decipher what this is. And the reason why they give it to you is it's a theorem is just, it works for everything. If I just give you an example, it works for one example. If the prof gives you a theorem, they're saying this works for every single case all the time. So I'm not going to fill in numbers, I'm going to fill in variables, and then that shows that it works for everything, just like trig proofs. Trig proofs, you didn't fill anything in. If you verified for one value. You filled in one value for all the x values, and you verified that one value worked. But when I wanted you to prove something worked, we always left x's in there, and we used all different theorems and different things from our formula sheet, right? Formulas. We plugged those in to get left side equal right side. Then it worked for everything, so you didn't plug in an x value. So, what does this mean? Well, it means that in order for a function to be even, when I plug in a negative x, I'm going to get the same y as when I plug in a positive x. Let's look at an example that isn't just variables. So if I looked at the y equals x squared graph, this is drawn terribly. This would not be a passing graph for me. I'm just sketching you something out. If I wanted it on an actual test, I would sketch with a lot of coordinates. Okay? So what this is saying is, if I plug in, that is an eraser. If I plug in the same negative x value as the same positive x value, I'm going to get y equals y. Same y's. That's all it's saying. This is just function notation for filling in a negative x. This is function notation for filling the same positive x, and then they're going to equal, which means the y's will equal. Okay? So if I plugged in negative 1 for the y equals x squared graph, if I plugged in negative 1, I would get 1. If I plugged in positive 1, I would get 1. So a y equals x squared graph is an even graph, because when I plug in its negative x and its positive x, I will always get the same y's. If I plugged in 3, I'm going to get 9. 3, I'm going to get 9. If I plug in negative 3, I'm going to get 9, right? So they're going to get the same y values no matter what negative x and what positive x I put in. It just has to be the same one. So a cubic function, a symmetrical cubic function, if I plug in negative 3, or let's plug in something smaller, I don't want to do 27. If I plug in negative 2 into a cubic function, I'm going to get negative 8. If I plug in positive 2, I'm going to get positive 8. Are those the same y values? Because they're going to be one's negative, one's going to be positive, so that's not an even function. So when you plug in your x's, opposite x's, and you get the same y's, that's an even function. That's all that theorem is saying. Plug in negative 2, plug in positive 2, I get 5 for both of them, cool. Plug in negative 3, plug in positive 3, I get 8 for both of them, even. If I plug in negative 3 and I get positive 3, and I get a negative 8 and a positive 8, that's not even. They have to be the same y's, same sign, same everything. Okay? All right. If I plug in negative 1 and positive 1, I'm only showing that it works for one number. If I plug in negative 3 and positive 3, I'm showing it works for one number. They don't want you to show that it works for one number. They want you to show that that function is even everywhere. So that's why we have to actually use negative x and positive x. Negative x and positive x. If I fill in negative x and I fill in positive x and I get the same y's, same functions, then that's even for all x's. If I just use negative 1 and positive 1, I'm only showing it for 1, 1, or 2, or 3. So let's try it out. So here it says, Is the function f of x equals x squared even or odd? Well, I already showed you it's even because I showed my little numbers, right? Did I verify that it's even? Yes. Did I prove that it's even? No. I verified for 2 values. They both worked. Yay, but I didn't show that for everything it works. So to show that everything works, if even, then the y values would be the same if you input x and negative x. So we test it out. So let's try it out. So I'm going to plug this into x squared, negative x, not a negative x, not negative 1, negative 2, negative 3, x. And then I'm going to plug x in for the other one. So let's see what I do. So f of negative x just means I rip the x off and I replace it with negative x. So I'm going to get negative x in for the x, but I'm going to have to square it. Oh, I have an eraser. Change colors. So I have a bracket squared, and instead of x, I have negative x for this one. We agree? For this one, I'm going to input positive x. So I still have the squared function, but I'm going to put in positive x. Do you see the difference of what I'm inputting? Just substituting it on opposite sides. Okay, let's see. Negative x squared, what does that result in? X squared. And what does positive x squared result in? Do I get the same y value on both sides, no matter what negative x and positive x I fill in? Yes. Now have I actually proved that this is even and not just verified for a couple of values it's even? Yes. So you have to fill in the negative x and the positive x. You can't fill in numbers. And that's when university math starts happening. You're like, what is this? They're proving for everything it works, not just 1 or 2, which is what we do in the past. Okay? So, because these end up being the same, we say the function is even. Therefore, when you do 3 little dots in a triangle in mathematics, that means therefore. Therefore, function f of x is even. It's an even degree, right? And it's even because it's symmetrical. Okay, the geometric significance of an even function is that its graph is symmetrical with respect to the y-axis. If I went to the y-axis and I split it, it would work. Yeah. Yes. So, what about odd? If a function f satisfies f of negative x and negative f of x, so what does this mean? This means this y value, say it's 8, what's this one going to be? Negative 8. And that's where you get that cubic function, right? It would be like this. That's all it is. So if we want to test for even or odd, we do it the same either way. If it's even, we would plug in f of negative x, f of x, and see if they equal, come out the same. For odd, we'd plug in f of negative x and negative f of x and see if they come out the same. And if they do, same y values, then they're odd. So let's try out this x cubed one. So we're going to plug it in here. We're inserting in for the x. So we're going to get negative x cubed minus, or equals negative, and then f of x is just x cubed. Do you see that? We're inputting in for f of x now. F of x is x cubed. What is negative anything to a 3? Negative. So what's negative x cubed? Negative x cubed equals negative x cubed. Do they equal? So then it's odd. So to test for even, you're plugging it into this. This tests for even. And when you plug it into this, this tests for odd. Now, what if you test both and they don't work? Then it's neither even nor odd. I always test for even first of all. So the geometric significance of an odd function is that the graph is symmetric about the origin. If we already have the graph of f from x is greater than 0, we can obtain the entire graph by rotating this portion through 180 degrees about the origin. If your head spins when you read things like this, welcome to university mathematics. they will have statements and statements and statements. And sometimes I would go home and just be like, okay, I'm overwhelmed. I'm going to ignore the fact that you just read that to me, Prof. And then I'd go home and I would reread it and try and make sense of it. Because sometimes just reading a sentence is overwhelming. Okay? So, we're going to try these ones out. So we're going to determine whether each of the following is even, odd, or neither. So if you want to test for even, you would plug in this in to f of x equals f of negative x and see if they match. If they don't match, this is for even. If they don't match, we can test for odd. Odd, you would fill in f of negative x equals negative f of x. If neither of those equal, then it's neither. You know what I'm saying? We'll do the first one together. Okay. So we're going to do the first one together. And I want to explain the odd one a little more, because even I think people get odd, they don't get. So if, say it was like this. Say if that's a negative cubic function or whatever, right? Say that's the case. Is this would be a negative x, would be restricted this way, and this would be a reflection but 180 this way. So you actually have to have it reflect and reflect in order to get it to go that way. One is reflected. So if I reflect this one, it would be over here. And then I'd reflect it again, I'd bring it down here. So that's why they're testing it with the negative x and then the negative f of x, because it causes a double reflection. All right, let's check for even. So even means I need to plug this in. Well, f of x is easy. It's literally just that, correct? So I'm going to get x to the 5 plus x. And then I need to find f of negative x, which just means I put negative x into there. So I'm going to get negative x to the 5 plus, and then instead of x, I have negative x. So here I get x to the 5 plus x, it's just f of x. And then here I get negative x to the 5, what's that? Negative x to the 5 minus x. Do they match? So that's supposed to be blue, not even. Correct? Now we plug it into the other equation. That looks like an x. It's supposed to be a wrong. Ignore that. I'm going to erase that because that looks confusing. Not even. That blue just made it look like there was another x. Okay. This one we do f of negative x. So we plug it in. Pretend we haven't done it already. So we're going to go negative x to the 5 plus negative x. And then I'm going to reduce this side so I get negative x to the 5 minus x. Now this one is easier. It's negative sign. I'm going to negate all of f of x, right? So I have to remember to put f of x in a bracket, because I have to negate the whole thing, not just the x to the 5. So I'm going to negate f of x. So I'm going to get negative x to the 5 minus x. Do they match? Yes. So this is therefore odd. That's supposed to be a perfect triangle. That is super not a perfect triangle. Okay, you try B and C.